Did anybody have any questions they wanted to go over first before we just finish up with the last couple topics? Okay. So if you have a question, I guess just let me know. Again, these are the topics. I think we left off on linked lists, so we'll talk about linked lists, doubly linked lists. I guess sorting linked lists, and then we'll just review stacks and queues really quickly, just because we did those recently. The other thing, let's see, there were two things I wanted to do before that. So there's a exam on, or not an exam, I guess that's calling it something fancier than it needs to be. There's an assessment on Canvas right now, and it's not for a grade, but if everybody could take it, that would be great. So here on Canvas, if you just go to the quizzes tab, there's an ABET assessment, and so it's marked as practice quiz. So it's not for a grade; it's just for accreditation. So you'll take these in any, probably engineering class, but any computer science class that you take. These are basically just here to make sure that you learn some of the outcomes from the course. Like object-oriented programming and all that. Uh, so give that a shot, and try not to Google anything. Try to take it just naturally. Don't look anything up. Try not to use notes. Just take it straight up. And if you don't do well on it, that's okay, because it's anonymous and it's also not for a grade. So um, don't worry about it too much. But if you could take it, I would appreciate it, because I kind of need as many of those as possible. Right. The other thing was, oh yeah, so assignment 10, just wanted to go over the write-up, which was pretty quick on that one, especially because one of them, I don't think you can even really answer that well. So I think there were two questions, and one of them was about the timing, and then the other one was in which case is bubble sort a good choice. And I just wanted to make sure we clear that up before the exam. So what were the operation times? These could be pretty much anything. I think the general consensus I've seen from students who timed the 100 was that it was somewhere between 3 to 4 seconds, and I'm sure some of that was, 3 to 4 seconds or 10, I think is the max I saw. So about 3 to 10 seconds. And that might vary depending on what's going on, like how many people are on Sally, or just the fact that it's maybe not, you don't have a whole lot of RAM, versus this requires quite a bit of it. And the big thing is that bubble sort, which we mentioned last time, is what you would call like an n squared algorithm. So the time grows exponentially. So if this is n squared, then if we went from 100 to 10,000, then this is 100 times bigger, right? Because 10,000 divided by 100 is 100. So if this is 100 times bigger and this is n squared, then approximately it's going to take you 100 squared times longer to run the second one than the first one. So if it took you on the low side, which was 3 seconds, times 10 to the power of, that'd be 4, right? Then it should take you approximately 30,000 seconds, which is pretty long, right? That's if we divided that by 60, then cancel a 0, and then this would be 500. Actually, 500 seconds isn't that bad. Maybe I'm dropped a 0 somewhere or something, but yeah, it should take you quite a bit longer. And a lot of you might be noticing that it took so long that you maybe just got tired of waiting, which was okay. I put that post on Canvas, right? That it was okay if you stopped timing it if it took longer than about 10 minutes or whatever it was. which is kind of what we expect. So it's going to be a lot longer in terms of runtime, and then there's also the fact that if you have more data, you're kind of prone to more hardware slowdown as well in a couple ways. So there's that. Anyways, the last few things that we had on the review were linked lists and then stacks and queues. So let's just discuss those again really quick. So a linked list, right, was just a series of nodes of some type. So generally we said it was a template class, because I think that makes the most sense, is not to strictly limit yourself. But in the example of assignment 10, that wagon was a node pointer that held specifically a string for a name of a company and then an integer for a load. So those were the data fields, right? And you can have as many data fields as you want. It just needs to hold data is the idea. So template, and then the generic type, let's just say, is T, and then we'll say node. Well, I guess it's a class node, or struct. I think a struct would be a better idea, just so that we can make it public. Struct node. And then we said that these always have a T for the data, and then a node pointer to the next node that they are going to look at. Semicolon, not period. And so the idea here was, if we wanted to make a linked list, it would look something like this, where we have the data field and then the pointer field, and it would always point to the next thing until we reach the end, which was always marked with a null. Right, so we put the data here, and that was pretty much that. And then we said if we are doing it this way, we can only traverse it in one direction, because all these arrows are just pointing to the next one. And so the idea was that we start at some sort of head. So we keep a pointer to the head in our linked list, which is the first node added at the beginning of the list, and then whenever we want to do anything with it, we just follow these pointers until we get to where we need to go. And this was a singly linked list, at least. And then we said it had three operations that most data structures have in general, which is insertion, lookup of some kind, or search or query, or whatever you want to call it. We'll just say lookup, and then a deletion. So we need to be able to, I am showing that right, deletion. We need to be able to put things into the list, we need to be able to look things up, and we need to be able to delete them. So let's just go through those three operators really quick. So, right, what we said is that by default, the head should be pointing to nothing. So if I start with a linked list that's empty, then there's nothing in it, right? So there's nothing there, which means it has no head to point to, because, I mean, there's nothing there by definition. But when we go and do the first insert, so what we said, every single time you insert, you want to create the node. So always create the node first. You want to set its pointer to equal to null, so that it's not pointing anywhere. And then you want to update the head, specifically on the first insert, because we don't have a head, to point to that new thing. So we always create a new node, adjust the pointer to point to it, and then, you know, we're done. So there'd be some data here. And then on the next node, we would do the same thing. So we would create it, set its pointer equal to null, and then update the last pointer at the end here at the tail. And then if we kept going, right, we would just add the next one, make its pointer equal to null, and then have it point to the next one. So that was the insertion, was we always insert at the end, and we've done the code before, so just I'll let you look that up, and just remember, right, we just follow these to the end until we get there, and then throw it on. And then lookup was pretty straightforward. So if we had something like this, then the way we've been doing it is with an integer, which I think is okay, but we could always do some sort of query, right, where we go through and check all the data fields and see if they match. So we'll say something like this. So the idea here was if we wanted to do a lookup where it was, let's just say get at a position, so int index, then all we needed to do is follow these pointers that many times, starting at the head. So if I wanted to get something at index 0, it would be this one, index 1 would be that one, and index 2 would be that one. So if I started at the head and I follow the next pointer 0 many times, then I would end up at the first node. If I started at the head and followed the pointers 1 many times, so if I followed just that one, then I would end up there. And if I started at the head and followed 1, 2 pointers, I would end up here at index 2. And the same goes for the rest of the numbers, right? So it was just start at the head, and while we're less than that number, keep going. And then so the other one would be, let's just say a search kind of lookup, which takes some sort of T data and then just checks. And so these would both be forms of lookup depending on how you decide you want to implement it. So the first one returns one of these nodes at a given point. I guess, so if we were to say like a return type, this would be the node pointer, and then the search returns whatever T is. Or actually, I guess you could say it returns a node pointer as well. That's all right. So, so this one, right, it goes through and checks if the data matches at each point. So this one would like traverse the list, start at the top, and hop its way down until it either reaches the end or it finds a data field that matches, in which case it would return that one. Or maybe its position or something, depending on what you want to do. And then maybe return some sort of sentinel when you don't find it, like null if you had a node pointer and you didn't find a node pointer that was correct. You could maybe return null, or maybe like, you know, -1 if you were doing integers and you knew the list was going to be positive or whatever you wanted. And then the last operation was deletion. And so this one was probably the most involved out of all of them, and it required us to do a little bit extra. So we had two specific cases for this. So first was if I go to delete a node in the middle, then if I just delete it straight up, so if I find it and then delete it, consider that this was still pointing to the data that we just deleted, so that was a no-go. So what we had to do was we needed to keep two pointers. We always kept one, which was the current, which was the one that we wanted to delete. So we would go through the list and keep two pointers. One that was pointing to the current node we were checking to see if that's the one we wanted to delete. And then we kept another one that was pointing to the previous. Right, so if I wanted to delete this one, what we said was we needed to update the next of the previous to be the next of the current so that it goes around it and ends up pointing in the right location. And then now the list is correct as far as its pointers, so we can delete this. And so now the linked list works again, right? This is the first and then this is the one afterwards. Now the one exception to that was if we went to go delete the head, because if we delete the head, then there is no previous before it in order to fix that and end up doing the removal. So what we said is you want to check first if you are going to be deleting the head and then do the special case if that's what is happening. So if I wanted to delete the head here, then what I would need to do is I would need to make the head point to the next one. So I need to make it point to the head's next. And then now you can delete this old head. And we'd have to keep a temp variable, right, for that if we were to actually program it. But the idea was that we redirect the pointer around and then sever the thing before it. Okay, and so the last thing I think to mention about singly linked lists is the reason we do this, there's two reasons. So the advantages of a linked list is that, so we said if you know you're going to be using a lot of memory and you think that you're going to have some issues with big blocks of memory, the nice thing about a linked list is that it's not contiguous in memory. So we don't require all the data to be stored right next to each other versus an array. So we said, you know, if I had this case where I had this as my memory space, and then I allocate a integer here, and then an integer here, and I say I wanted to make an array of size 3 that is not doable anymore when I go and use a array. Even though I have 3 open cells, I can't actually go and put things into it because they're not all next to each other. An array has to be next to each other, so this doesn't work. But if I use a linked list, aside from the fact that it consumes a little bit more memory, it does actually allow us to put them not next to each other, right? So that was one of the advantages. And then the other advantage I would say is that it's easier to implement certain data structures. Using a linked list, or specifically nodes, you'll learn later in the actual data structures class when they go over trees, that it's a lot easier if you just use nodes instead of trying to make it into an array. So specifically for this class, the queue that we went over later I think is quite a bit easier and not limited when you use a linked list versus if you use an array. And even a stack, I guess, is kind of nice to have it like that too. Although I guess we could do better with that in C++, I would say. Right, so the disadvantages then were it took... maybe I should space that out a little bit better. So while the memory is not continuous or contiguous, we do have to worry about the fact that it stores a pointer along with it means that it does take up more memory, because that pointer is added on in addition to the data that we're storing, and lookup is way worse. I mean, it's not terrible, but it's we have to go through the whole thing, right? And so I think those are the main points to take away from that. Okay, and then the other stuff that we went over were doubly linked lists. And then I'll just mention circularly linked list. We didn't go into a whole lot of detail, and I don't think we will again, but remember that a doubly linked list, the only difference was instead of always just pointing to the one next to it, it pointed to the one next to it and also to the one before it. So if I had a bunch of these doubly linked nodes, then they still keep a data field, and then they just keep track of both the one before and after them. And the reason you do this is so that you can point backwards and get the node before you, and that makes certain operations a little bit easier. So we still kept a head, and we could keep a tail here if we really wanted to, but we'll just say we'll keep a head, and then remember there's a data field just like there was before. And so the idea with this one was just, well, it's slightly easier to manage some things because we can look in both directions, and this might help us a little bit in terms of being able to move backwards or do things that require us to move backwards. And you'll see a lot of the time when you do nodes, usually you do them with two pointers like this. The singly linked is not incredibly common, I would say. I mean, I would assume that's how most people implement a queue, but And again, so there was the insertion, lookup, and deletion. So lookup is the same as it was in a singly linked list. So we can just start at the head and work our ways forward until we hit the thing. And so there's nothing really different about that, right? Because we still have the ability to go forward, and there's nothing special, there's nothing extra required there, because we don't need to update anything when we do a lookup. We just get something and return it. So the fact that we have an extra pointer doesn't really mean much. But the idea with insertion was that we just have to update one extra pointer now because we have one extra pointer. So the head insertion was the same, right? I mean, it should be, because we're just inserting a new thing into an empty list of some kind. So we go here and we create a new linked, or we create a new node, and then recall that this would be null when we start, and then once we go and insert the thing, we set it to be here. And then, like the end of a singly linked list being null, the head of if a doubly linked list is the previous is going to be null, because it's going to mark the beginning. So here we'll have the left hand side equal to null, and then we said that the right hand side we're going to make null as well because there's nothing there. And then again, as we go and do the insertion, we always create a new one and then set its nodes. So we always set these nodes to null by default. We said was the easy way. And then here we would need to set both of these pointers. So when we go and do an insert here, we'll need to set the previous one to point to this one, which is what we're used to, right? You just go to the end, make a point to it. And then also for the new node, we have to have it point backwards to that last element, the tail element. So for this one, right, we would do the same thing. We would set both of its pointers to null, traverse the list, update this so that it points there, update that so that it points there. Right, so that was the insertion. And then the deletion was very similar, but the nice thing about doing deletion in a doubly linked list was the fact that we don't have to keep two pointers because of the fact that we can look backwards, so we don't need to keep that previous like we said for the other one. Right, so if I kept this and kept that, and then let's just say I want to delete the middle one, and this was the head again. So the head is basically the same, right? The deletion of that, we have to do a special case where we just delete it and then make the head point to that one if we wanted to do it that way, where if we were to remove the head. And then the only difference on this one is that we would need to update this back pointer to be null, but we already have a pointer to it, so that's not a big deal. And then the idea, if we wanted to delete one from the middle of the list, is now we don't need a previous one because we always have a way to point backwards to it. So we would look at the previous one, have it point to the next one. So we would rearrange that pointer. We would look at the next one, have its previous point to the one around it, and then now this node is kind of severed from the list, right? The things around it point to the right location, so we can delete it. Any questions so far on the singly or doubly linked list? I'll let you type if you do have a question. But so the last thing that might show up on the exam would be a circularly linked list. And so the only thing about a circularly linked list was that it points to not null at the end, but rather the beginning again. So if I had a linked list like this, then rather than make this point to null, I would have it go and point back to the beginning. And the reason you do this is just so that if you reach the end, you can circle back around, and we don't have to worry about that whole issue with backtracking. And we could totally have this with a doubly linked list as well, if we wanted to. So if I have this point there and this point there. That point there. Then it would basically do the same thing, right? This would need to point to there, and then the only difference is that since we have a back pointer, rather than this point to null, it will point to the end. And this is just nice if you need to be able to wrap around for some sort of reason. Kind of make like a stack of pancakes looking shape here. But it makes traversal a little bit easier, and you've probably noticed from trying to implement insertion sort, I think a lot of people have struggled a bit with that on the last assignment, is that it's a bit difficult to do that because you would need to go backwards, and we can't really do that in a singularly linked list, and we can remedy it a little bit if we use a circularly linked list. Right, so I think that's everything about linked lists to mention. And the last thing we went over was stacks and queues. So recall that we had two different data structures, a stack and a queue. And the difference was really just the order they insert things. So if this is the top and this is the bottom, or you could say front and back if you wanted to, then if I was to go and do both of these and say I want to insert three things, then what we said was, if I go to insert something into a stack, the way it works is that it always goes to the bottom first, whereas a queue it always goes to the top or the front first, and then when we insert things, we keep doing the same thing. So stack always goes to the bottom, or like the lowest open spot, or in other words, you could say it's the top of the current stack. So here the top of the current stack was A, right? We throw a B on top of it, and then a queue we always put it afterwards. So the idea with a stack was that it looks exactly like you would say like a stack of blocks or a stack of plates looks like in real life, where you always put the newest thing and you stack it on the very top of everything else, and you don't really just insert it into the middle. You always put it on the top if you don't want things to fall over. And then a queue was like a line in real life, so you go to a restaurant or a store or whatever, and everybody stands in a line, and whenever somebody shows up, they always go to the back of the line, and the first person who got there is always the first person that gets served. So a stack, we said, was an example of first in, last out, and a queue was an example of first in, first out. Sorry, this would be last out. And then this was first in, first out. So the idea with a stack was that the last thing that showed up was the first thing that's going to leave. I guess that would be kind of flipping around the reasoning there, but it does hold. And a queue, the first thing that showed up is the first thing that's out. And so we said a common use of a queue might be if you want things in order. So, I write some sort of queue for, people showing up to a restaurant, or messages that I need to display to the screen. Then I should display those messages in their order. I guess actually there's one thing I didn't mention, which I'm not sure if we're supposed to talk about, but I will anyways. So there's actually also like a notion of like a priority queue. Maybe I'll actually talk about that for a moment. Let's talk about normal queue again really quick. So if I had a queue and object A showed up, object B showed up, and then object C showed up, over time. Then the way it would work is A would go to the front, B would go behind A, and then C would go behind that, and then so that would be our on cue, as we said, that was the word. And then when we try to take them out of the line, then so let's mark this really quick. So this would be 0, 1, and then 2. And then when we go to DQ them, they leave in the exact same order. So A leaves first, B leaves second, and C leaves last. So they show up and leave in the same order that they got there. So there is a slight variation of that, which I don't know if that's in the scope of this class or we're supposed to talk about it somewhere else. I usually think it's discussed in like operating systems, but there's also a notice or the notion of a priority queue. What did I hit to do that? All right, no idea what happened. There's an idea of a priority queue, which is that you assign maybe like a value. So let's just say these are customers again, or messages, I guess would make a lot more sense. So these are messages, or in the context of operating systems, it's usually programs or processes that you're going to be executing. And these all have some sort of value. So maybe this has 4 and then 6 and then, well, actually we'll say this one's lower. 4 and then 6, or sorry, 3 and then 6. And so if A showed up, we would put A at the beginning of the line. And then if B showed up, we would put B at the beginning of the line, or B after A. But if C showed up, what we would do is, because C has a higher priority value than the things before it, it would get to cut in line. So it would jump there and then jump there, and now C gets to go in front. So the idea with a priority queue is that if you have a higher priority, you kind of get to cut in line to anybody that has a higher priority than you. So you can think of it like it's a sorted queue, and you could do this in different ways. Maybe, you know, if you only wanted to skip so many or something like that, but you can give them a priority and give them the ability to kind of cut in line depending on like a high priority or a low priority or whatever. And so the only real difference between that and sorting everything is that we're doing this in some sort of running system, right? So things might be happening like concurrently or at the same time. So so if something shows up, then it has the ability to cut, but you know, not everything is going to show up before things leave, right? So I could say maybe something happens and then C is DQ'd, and then I get a new thing D and that shows up. So the difference here between it and being sorted is that this is constantly changing, right, over the run of whatever program that you're running. So that's the main difference, and that's the reason it's still kind of a queue. I don't expect that to be on the exam, but I figured I would mention it just because I remembered it right now. Just in case. Might as well. So it would be queue, and then the stack, the idea we said with that was that the first things that show up are the last things that are going to leave. So, you know, if A showed up, and then B showed up, and then C showed up, A would go to the very end, and then C would be at the beginning. So they kind of go in the reverse order if everybody just shows up and is added to the stack. And we said that adding things to a stack, that was called pushing to the stack. And then when they leave, then they go in the reverse order. So C gets to go first, B gets to go second, A gets to go last. And we call that operation popping. And so the idea with that was that a stack is able to reverse things. So we gave that example that one time about reversing a string. Or you could also say, if you're going to not put everything in at once and just kind of keep it running, like maybe concurrently with something, then keep a history of some kind. And so the direct example we gave for that was that, you know, if you go and you start up whatever web browser you want, and it has the search bar, and then it has the little back button, and that's all we really need here, then if I was to go to, let's say, Gmail, and then I go to Web Campus, and then I click on announcements or something like that, then every new page that you open gets added to the top of the stack. And then whenever you go and you click on this little button here, then that says to pop from the stack. So when you hit the back button and you're on the Web Campus Announce page, right, it's going to take you back to the last page you were on, which was the Web Campus main page. And then if you hit the back button again, it would pop that off the stack, and then we'd end up back at Gmail, right? So the idea is that it keeps a stack, and that if you use it that way, you can keep a history that you can go back through if you decide to pop from stack. And so it does keep a forward pointer as well on your browser, but the general methodology with the stack is that you should only be able to work in one direction. So this pop is just going to work our way down the stack. And then the other thing we said was, if we go and open a new page, it will overwrite this. So maybe I go to Google and just Google computer science or something, or I'll just say computers. And so it would open a new page and it would put it onto the stack, and we would keep track of, again, where the top of that thing is. So let me make that look a little bit nicer, because I'm going to have to post this later. Pop. And then the other example that's very, very common and that you should know for sure, I don't know if we're going to do it on the test, but it's good knowledge for computer science, is that when we write code, so if I had a void function called foo that did whatever, and then I had a void function called g, and g calls foo, and then I go to int main, and I call g. Then as far as the execution of this program goes, programs always start at main. So we would start here. It would see this, actually I guess let's take it one step at a time. So it would start in main. So the current function being executed is main. And then it goes down and it gets to this line of code and it says, okay, I'm going to go execute G. So it jumps, right, is what a function does. It just jumps to where that location is of the code. So we'll jump up here and say, okay, I'm going to go execute G. So now G is the current function being executed. And then while we're in G, it will get to this first line of code and it will say, okay, I gotta go call foo. So it will jump up to here and call foo. And so whenever it does function calls, it will keep a stack of everything that it's called. And then the way we return things, right, is once foo is finished, it has to go back to G. So once foo is done, it will pop itself, go back to G. And so it knows what function it's in, because the function that it called from, right, is always going to be the next one on the stack. So if foo finishes, it knows, oh, G's the one I got to go back to. When G finishes, it will pop and it will say, okay, I know that main's the one I got to go back to because that's the last one on the stack. And that kind of makes sense with what we were asserting earlier, right? The idea behind a stack is that it keeps some sort of history, and really what you're doing when you're returning from a function is you're just following back the history of the function calls that you've had. And this is the reason why you'll see the term stack overflow. Is because if you call too many functions and this stack ends up growing too big and takes up too much memory, then this whole stack just breaks and we can't do anything else. So if you use too much memory, then that happens. So too many function calls. I keep hitting something on this pen that's making me go to different pages and do weird things. All right, here we go. So too many function calls will get you a stack overflow because you'll end up putting too many things on that. And the name of this here is the call stack, which you'll see in your debugger if you use Visual Studio. It will let you look at the call stack, and you might even see it if you get a error while executing and you're using a debugger of some kind. It will say, oh, here's the error, here's the call stack, which is very helpful because it tells you what the order of functions that was called was, which, you know, might be nice if you're trying to figure out what's wrong with your code. So the last thing, I guess, would be how do we implement this with a linked list? So again, a linked list has some sort of head, and then as we insert things in, we put nodes in and then have them point to the next one, and we keep inserting to the end. So the on queue of a queue is really just the normal insertion that we're used to. So we start at the head and follow our way down until we hit the end. So on queue is just normal insertion. There's nothing different here. And if we think about it, that makes sense because when you get into a queue or a line, you always go to the end of it. So normal insertion at the end. And then when we dequeue, what we need to do is remove from the front. Which again, I think makes sense with the queue. Normally when people show up, the next person in line who gets to go is the person at the front of the line, not the person at the end of the line. So what we would do is we would just make the head redirect, and then we would return this part. So that would be for the dequeue. So queue almost basically the same, not too hard to implement with a linked list, which is nice, and that's kind of the reason I think you would use a linked list for this over an array, is because this is pretty simple, right? This is 2 lines of code, and this we've already written before. And then we could also do a stack with a linked list, although I think it would be better to do that with contiguous memory. And that's generally the way it's implemented from like a systems perspective. But again, if we have some sort of head, we always insert at the beginning of that, right? There's nothing different there from a linked list. But the idea is when we push onto a stack, that rather than insert at the end, we will insert at the head. Which kind of goes along with our mantra of a stack, which is the fact that you always add things to the beginning and then also remove things from the beginning. So when we do an insertion here, it's actually a little bit faster because of this. We would just create the new object, have it point to the current head, and then redirect the head so that it now points to that thing. Maybe for the sake of the drawing, let me just scribble that out. There we go. Right, so the difference here is that rather than insert at the beginning, we insert at the end. And again, not too too hard here, right? We just need to make it point to the head and then redirect the head around it. And that's kind of helpful, right? Because it's only 2 operations and we don't have to search through the whole list. So I would argue that it's easier to do the insertion here than in a queue or a normal linked list. And the pop we said was just the same. So same as queue, we just remove the head. So again, all that would mean is that we make this point back to the next one, and then we sever that and return the value. So I think that's about everything we talked about as far as those goes, and I think that's about everything as far as the class goes. So were there any final questions or anything that you wanted to go over again really quick? Will there be any work-throughs for the final assignments? Maybe. So it might be a little bit rough because I mean I got like 2 weeks left, and I mean I'm a student too, so I still have finals. So I'm not sure if I'll have a whole lot of time. I mean I don't have to take final exams, but I have to work on stuff. Maybe. I'm not sure if there's any specific assignments we want to work over. I mean, I could do it after the semester's over for sure, but I'm not sure how many people would be interested in that. But I suppose I could. I'll have to think about it. Depends on how well things go the next few days. Was there an assignment in particular that you wanted me to work through? The doll one or the 10th one? The train? $10, $11 mostly. I can do 10. 11's due finals week anyways, but I can share the code. I already wrote 11. I mean, I wrote 11 because that's the assignment I was in charge of writing. I can share that after the fact. Or did you mean just work it through? Oh yeah, I mean I wouldn't do 10 for a while anyways, but yeah, I mean I can write 11 at some point, or at least I can post the code on Canvas afterwards. 11 is, I think, one of the shorter assignments. There's maybe like 4 or 5 functions to do, and most of them are like 1 or 2 lines of code. I tried to make it easy, just so you have more time to study for the final. Any other questions with regards to this or the final? And then I guess my other question would be, if not, is there anything in particular that you wanted to talk about? I mean, we got 25 minutes left, or do you have a moment to talk? Yeah, I can talk about it. Just, I guess, after we end. That's okay. So I'm gonna assume no other questions. Did you all want to talk about extra things in like preparation for future classes, or would you rather just end early? Is there tutoring next week? I assume the tutoring center, whatever they have, like a virtual tutoring center, is probably still open for finals week, I would imagine. I'm not too sure though. I would double check the UNLV website. Well, if nobody has any other questions, and I'm not seeing anybody saying in particular that they want to go over things, so I guess we'll just end early, and yeah. So I guess that's the end of the semester. The exam, just final reminders on Monday at 10:10. I should probably write that down. Oh, that's not the thing. Okay, there we go. It's Monday, December 7th from 10:10 to 12:10, and then it's on Canvas like you'd expect it to be. Okay, well then, I guess I wish everybody the best of luck on the final, and if you have questions before then, feel free to send me a message. And the final program, assignment 11. I don't know how I keep hitting that. The assignment 11 is due on Saturday, which is, today's Wednesday, so Thursday for the 12th. So just make sure to get that in. Right. Definitely no. I'm just going to preface it on these last two. No extensions, because we're really close to the end of the semester, and I kind of need time to be able to grade them and get them submitted. So, no extension for sure. Due on December 12th. Again, this one should be pretty short, so don't worry too much about it. And I think that's about everything. So then, I wish you all the best, and if you have questions, just feel free to message me before the exam.